Good morning, guys. Today we're moving on to lesson 11.2, day 1, translating rational functions. Basically, all that means is we are going to be graphing them in a new place in the coordinate plane. They're going to shift left or right or up or down or something like that's going to happen. So today is Wednesday. We're going to do this lesson day 1 today. And when we're done with this lesson, hopefully it's a short lesson, you can do problems 1 and 2 on the try on your own. And tomorrow we will do day 2 of this lesson, which should go pretty short and sweet. And then you will be able to complete the rest of that 2.1 try on your own, or excuse me, 11.2 try on your own assignment. And then please make sure you send in your homework by midnight Monday night for 11.1 and 11.2 on Monday night. So what I got here is just remember that as we are moving through here, anytime I'm looking at these parent functions where the degree of that denominator is going to be an odd function or an odd degree, what that means is if I put a negative number in there, okay, when I take a negative number to an odd power, that is going to keep that number negative. So that's kind of placing that one branch down here in quadrant 3. And when I put a positive in there, a positive divided by a positive is going to be a positive, and I'm going to be up in quadrant 1. Now, whenever I'm changing that function in the degree of that bottom is going to be an even degree downstairs in the basement, well, what that means is I'm always going to have a positive, and even if I put a negative number in there and take it to an even power, I'm going to have a positive divided by a positive, so that's going to place me up here in quadrant 2. And when I put a positive number in there and I take that positive to a positive number, I get a positive over a positive, and that keeps me in quadrant 1. So these are just the general shapes, okay? These are all different parent functions here, just so you know. Each one's different. This is the mother of most anything with a first degree in the downstairs, okay? And that is just the general shape. Remember, they have the same horizontal and vertical asymptotes. They do not have the same range. Their domain is the same, but the range is different on both of these, okay? So the range on the right-hand one there, okay, where my bottom is even, my range over here is going to be all real numbers, y greater than 0, because I can't get any negative outputs out of that, all right? So just keep that stuff in mind. From here, I'm not even going to really do too much on the bottom, but I will on the bottom, so I'll talk about that here in a second. We'll talk about the end behavior, but find the domain of each of the following rational functions. That means find what you cannot put into this function and still get a y value out. So I'm going to hit pause, and I will be back here in a second, and I will have all the answers. So as you come back, please don't overthink any of this, all right? When you're finding the domain of a rational function, or basically a really gross fraction with x's in either in the numerator and denominator, or just the denominator, remember what we are trying to do is we're trying to find out what values I cannot put in there. And remember, we cannot divide by 0. So all I do is I take that expression that's in the denominator, I set it equal to 0, and whatever will make that expression 0, those are the values I exclude that can't be there. Like here, I have x plus 5. Well, if I set that equal to 0, well, when x is negative 5, I get 1 divided by 0, so I restrict that, so the domain is all real numbers except x equals negative 5. And the last one, I'm just taking that expression, and I'm setting it equal to 0, and I'm just solving a basic algebra equation. And once I find out what makes that denominator 0, I exclude it from the domain of this whole function, okay? The other thing we're going to be talking about is we need to talk about end behaviors, and we've been talking about end behaviors because horizontal asymptotes, right, these guys right here, they are called end behavior asymptotes. And so what I'm thinking of whenever they're asking you where is the horizontal asymptote, I need to think of an end behavior. I need to think as x gets really, really big, what happens to this when I put a very, very large number into this? Well, what happens if I take the number 3 and I divide it by something that is getting bigger and bigger and bigger? Bottom line, it's a positive 3 divided by a positive large number, that's going to give me a very small number that is getting slowly but surely approaching 0 from the top side. Okay, so all I need to do is I need to picture a very large number in there. And as I'm finding my left-hand end behavior, so as I go to negative infinity to the left, okay, that's this way, I can see if I take 3 and I divide it by a negative large number, what I do is I end up getting a negative small number, which is slowly but surely approaching 0, but it's because it's negative, it's approaching 0 from the bottom side, okay? So those are going to be my horizontal asymptotes. This is going to have a horizontal asymptote of y equals 0, because that is what these end behaviors are approaching, okay? So what we're going to do is we're going to come through here to this next one, and little shifty behavior, take 1. Okay, recall from the previous section, the reciprocal powers have vertical asymptotes at x equals 0 and a horizontal at y equals 0. The domain is all real numbers except for 0 because division by 0 is undefined. That's what I just did. In this problem, what we're going to do is we're going to use Desmos. If you need to use Desmos, you can use it, to explore rational functions of the form 1 over x minus a number for a constant value c. So what we're going to do is we are going to look here, and we're going to see, and you can type these into Desmos, or you can use a little bit of logic out of them. So what I'm doing is I'm thinking about vertical asymptotes. Vertical asymptotes are when my denominator equals 0. So whenever x minus 1 equals 0, or when x equals 1, that is going to be a vertical asymptote because that gives me an undefined value in the denominator, okay? And that undefined value for my domain would be all real numbers x, and I have to exclude that from my domain because I can't divide by 0. But vertical asymptotes are basically, in a nutshell, 99% of the time, a vertical asymptote is whenever you divide by 0. Now, notice I said 99% of the time, not all the time. Horizontal asymptotes. Horizontal asymptotes are simply thinking, as I'm going to the right or way out to the left, what is my function getting snug as a bug in a rug to? Well, I'm going to give you a little clue. Rational functions can have at most one horizontal asymptote, okay? They do not have to have one, but a great deal of them do. And all I'm going to do is I'm going to picture in my head as if I put in a very large positive number for x, I'm going to be taking 1 divided by a large but positive number. And if I take 1 divided by a large number, that actually gives me a very small number. And the bigger the denominator gets, the smaller that fraction gets, which means it's approaching what? Well, as it's getting smaller and smaller and smaller, it's approaching 0. So my horizontal asymptote would be y equals 0. And if I have a horizontal asymptote at y equals 0, well, then I'm going to have that not necessarily an exclusion in my range. And then to find your range, you are definitely going to want to see your graph here, which means you really want to pull up Desmos here, and we're going to add a graph really quick. And I'm going to take this first one, and I'm going to make a fancy fraction of 1, and I'm going to divide that by x minus 1. And I'm going to look at Shazam. Hey, I can see I have a vertical asymptote right here at x equals -1, because I can see I'm going up and down there, and I can see horizontally I'm getting snug as a bug in a rug to 0 from both the top and the bottom there, okay? So that's what you're looking for. You're just going to graph these guys, and you're going to say, hey, where's my vertical asymptote? Where's my horizontal asymptote? And I can look at this graph, and I can see the range of this graph is all real numbers y except 0, and the domain are all real numbers x except for 1. So that's all you're going to be doing there. And, uh-oh, what did I just do? And it's going to be there. I hit the wrong button. And what I'm going to do is say my range here is all real numbers y except 0. And what I'm going to do is I'm going to hit pause, and I'd like you to knock these other three out in Desmos quick, and we're going to see what's going to be happening here, all right? So as you come back here, okay, you can just check out this table that I got going on. I filled it out, and in the second one there, 1 over x plus 2, I can see I'm going to have an undefined value at -2. That's why I have a vertical asymptote at -2. Horizontal asymptote, you can see there is going to be y equals 0, which means my domain is everything except -2, and my range is everything except for y equals 0. And as you're going through here, if you actually went through it and you graphed all these, hopefully you're connecting a couple things here. The first thing is, notice all of these values for x that we have down here in the denominator. Number 1, they're to the first power. Number 2, they do not have a coefficient other than the number 1. Okay, so it's really easy to solve. So this c value here, whatever it is, if c is 1, my vertical asymptote's 1. If c is -2, my vertical asymptote is -2. If c is 5, my vertical asymptote is 5, because that's what gets me in there. But be careful, because when I see x minus 5, I got to think, what value for x do I plug in there? I plug in a positive 5, not a -5, to find these vertical asymptotes, right? And then I'm just reading my graph for the horizontal. I can algebraically find those horizontal asymptotes real easy, but to find the range, you're really going to want your graph for this point in time, right? So what we're going to be doing here in this little next part is determine the vertical and horizontal asymptotes of the following rational functions without using a calculator. Then verify on your calculator. Well, bottom line, vertical asymptotes happen when the denominator is undefined, okay? So how do we do that? We take the expression in the denominator, x minus 6, we set it equal to 0, and whatever x equals that makes that 0, hey, that's my vertical asymptote. So I have a vertical asymptote at x equals 6 for that first one. My horizontal asymptote, what I'm thinking about is I'm thinking about putting a large number in, subtracting 6 from it, and what that's going to do, that's going to give me 1 over a positive large number. And as that number gets bigger and bigger in the bottom, this is getting closer and closer to 0, so my horizontal asymptote would be y equals 0. Okay? Why don't you do the next two, and I will be back with the answers. So as I come in there, obviously I set my denominator equal to 0, and I'm thinking, oh, -3 makes that undefined, so my vertical asymptote's x equals -2. Well, horizontal, just understand, it really doesn't matter what number is in the top, because as the bottom, the top is constant, okay? It never changes, but what's happening as I'm putting bigger and bigger numbers in for x, this number gets bigger and bigger, bigger and bigger, and it's going to slowly take a number that's not changing, dividing by 1, that's getting bigger and bigger and bigger, slowly gets closer to 0 and 0 and 0. So as long as there's not a variable in the top, your horizontal asymptote's always going to be y equals 0. And the last one, vertical asymptote of x equals 2, okay, and horizontal of y equals 0. Well, let's determine the general formula to identify the vertical asymptote of a rational function in the form g of x equals a. A is a constant. It's just going to be some number divided by x minus c. Well, if you follow the rules of engagement that I give you, if you take that whole expression in the denominator and you set it equal to 0, it's going to be very easy to see x equals c, because I got to add that c across. It's going to be x equals c. Now, if you had one that was x plus c equals 0, well, then that would be x equals -c, wouldn't it? So don't just look and say, whatever this is, that is my vertical asymptote. Actually set that bugger equal to 0, take a really short time to solve it for 0, and then write the vertical asymptote. And if I have a vertical asymptote there, remember, I can't take something and divide it by 0 because that's undefined. So that vertical asymptote that I have there, my domain, is always going to be all real numbers x, except whatever that c, or there could be more than one, whatever those values that make it undefined are, they need to be excluded from the domain. And The range of this is if my top is constant, okay, like I said before, what's going to happen is the denominator as x gets bigger and bigger and bigger, and I don't care if it gets bigger and bigger positively or negative, this bottom number down here is changing and it's getting huge, okay, and it's always changing, it's getting huge, which means this is sooner or later getting tiny, which means y equals 0 will be my horizontal asymptote, right? And as we're cruising along here now, without a graphing calculator, determine the domain, range, vertical asymptote, horizontal asymptote of each rational function. Well, my domain. Well, I would never do this. I would never do my domain first. I would always find my vertical asymptotes first, because I can look at this and I can say, hey, if x equals 0, that makes this thing undefined. So I have a vertical asymptote when that function's undefined. If I'm undefined on a vertical asymptote, my domain, it's going to be all real numbers x except that those undefined values, okay? And also, as I'm looking here, as I'm seeing this is going to be g of x, the bottom is changing, it's getting bigger, so 10 is getting divided by a number that gets bigger and bigger and bigger. Hey, that's talking about my horizontal asymptote. So that's getting closer and closer to 0, but it's a horizontal line, so it's y equals 0. And I can also think my range, okay, this is going to be, because that bottom is to an odd power, it's to the first, I can kind of think my graph is going to kind of look like that in the quadrants 1 and 2, which means my range is going to be all real numbers, y except 0, all right? So I'm going to actually hit pause, do these next two. Why don't you give them a try? All right, so as I look down there, I can see my undefined value is going to be -10, so I start with my vertical asymptote. Second thing I do is I picture in my head, well, this is going to be 6 over large number, and the number in the bottom is getting larger as x gets larger, which means y is getting closer and closer to 0. It's getting snug as a bug in a rug to 0. Well, if my vertical asymptote is -10, that's a danger area, which means I need to exclude that vertical asymptote from the domain, because if I plug that vertical asymptote value into my function, what happens is I'm getting 6 divided by 0, which is undefined, and we can't do that, nor will your calculator. Okay? And then my range, because I can see the degree of this bottom is to the first power, I can see it's going to be a graph that is in both quadrants, top and bottom. And it's a ditto for j of x there is the same thing we're going to come through, all right? And then the last thing we're going to do here is we're going to write a rational function from the table or description provided. Well, hey, if I have a vertical asymptote at x equals 3, that means I am undefined at x equals 3. That means I'm dividing by 0 when x is 3. Well, how would I divide by 0? Well, if I have x minus 3 in the bottom, I'm going to divide by 0 if I put a 3 in there, right? And if I have a horizontal asymptote at y equals 0, that means as I plug a very large number in for x, my fraction's value is going to go to 0. So I can put any number I want, just a number, not a variable, in the top, okay? So if I know in part B, if my domain is of all real numbers except -2, the only reason x equals -2 would be excluded from the domain would be because it's undefined at that point. So I'm going to make myself a fraction, and I'm going to say x plus 2, because if I put a -2 in there, now I'm dividing by 0. And if the range is of all real numbers except y equals 0, well, hey, that just means my graph is going to kind of look like this in a way, or if it doesn't look like that, maybe it looks like this over here, okay? Oh, it's not going to look like that because I'm going to have an asymptote there and let me draw that up there quick. Let's just make one here, and it'd be 1, 2. So I'm going to have a vertical asymptote here probably at 2, and that just means my graph would look like this if my range is all real numbers except for that, and like this, okay, or it might look like this, okay, which means I just have any old number I want at the top, maybe a 3. Doesn't matter what number it is, okay? Now, C, Letter C is a little bit different. Now I'm focusing in here and I know I'm undefined, which means I get 0 and I don't know what's in the top, but I do know I'm going to get 0 on the bottom if I put 2 in, so that means I want to see an x minus 2 because 2 minus 2 is going to give me 0. However, notice this is very specific data. I don't know what number goes in the top. Okay, so I'm going to think about this a second. And then from there, I'm just going to pick any old random thing I want. Now remember this is an x column and this is a y column. Well, that means if I use this point, if y equals -1, then what is a, that's a bad a, when I take 0 minus 2? Okay, well, this is going to give me -1 equals a over -2. Well, this is over 1. If I cross multiply, I find out a equals 2. And if a is 2, this is just a nice algebraic way to do it. I'm just going to come back and I'm going to say, hey, 2, there is my function. That's going to give me all those data points out. Okay, it's the only value that I can put in the top that's going to output all these numbers that I need. Okay, and then part D is just doing the same thing, except now they're not giving you a table, they're giving you a graph with some points on it. Well, what do you notice? Hopefully you notice I've got a danger area right here at -3. So I want to see if I put a -3 in there, if I put an x plus 3, so if I put a -3 in there, I'm going to get something over 0. Well, I don't know what goes in the top, okay? But that was very kind of them. They did give me a couple points here. So all I'm going to do is I'm going to grab, say I grab this point right here. And that's an ordered pair of 1, or -2, 1. Well, that means when y is 1, okay, I have a over plus 3. That means -2 is my x value. So what's that going to give me if I go across? Well, that's going to be a over 1 equals 1. Well, that just means a equals 1. So if my a value here is 1, that is going to be the only value for x that is explicitly going to give me that exact graph going through both of those points. I need a particular value for a. It's not just saying like the first two, hey, I got a vertical asymptote here and a horizontal asymptote here. That could be an infinite number of graphs. As soon as I get data-specific stuff, then I need to find that exact value for A. Hopefully this made sense for you guys. And you don't have a lot of work to do tonight. All you got to do is numbers 1 and 2 on your try on your own, and we will finish this section up tomorrow. And after that, you'll be able to finish the whole homework assignment. Have a great rest of your day.